This is Schlieren visualization of shockwaves in supersonic flow. I'm Chris Painter.
I'm Mark DeCesar.
I'm Eric He.
And I'm Nitika Yadlapalli.
As an outline for our project, we'll be starting with background information on shockwaves, Schlieren, etc. Then we'll move on to the procedure behind our wind tunnel testing of both the cone and bud shape models that we made. Finally, we'll present our results and analysis of our results based off theoretical values, and we'll finish with our conclusion.
Alright, so some background. In order to understand our project, you need to understand what a shockwave is and how shockwaves are created. So first off, there's something known as the Doppler effect. So when a source that's emitting sound moves in a certain direction, the frequency changes depending on how fast the object is moving. And as you can see in the picture on the left, this source of sound is moving to the right, and you can see that the waves in front of the source are compressed while the waves behind are kind of expanded. And this effect becomes more noticeable at higher speeds. So if you go fast enough, if you hit a certain speed, which is the speed of sound, and you go past the speed of sound, this effect becomes so exaggerated that the waves actually begin to overlap. And this overlapping creates a kind of a cone, conical shape this way, and it's known as the Mach cone. And this is the most basic type of shockwave that you can experience. Alright, so in order to better quantify our flow, we introduced something called the Mach number. And the Mach number is the velocity of the flow, or the object, divided by the speed of sound. So it's basically how fast the object is moving with respect to the speed of sound. And using this Mach number definition, we can quantify 4 different flow regimes. First is subsonic, where the Mach number ranges from 0 to 0.8. Next is transonic, where the Mach number ranges from 0.8 to 1.2. Next is supersonic, where the Mach number is greater than 1.2. And next is hypersonic, where the Mach number is greater than 5. And, alright, so in our case, the wind tunnel we're using at Rutgers, it runs at Mach 3.45, which is supersonic speed and will consistently generate shock waves. So how does the wind tunnel work at Rutgers? Well, or any wind tunnel in general. Well, first we define something called compressible flow. And the main thing to remember about compressible flow is that the density of the flow is not constant. So, as opposed to incompressible flow where the density remains constant throughout. So, how the wind tunnel works. So we start on the left, and it's called the convergent divergent nozzle. So the left side of the nozzle is convergent. So the cross-sectional area decreases as you traverse along the left side of the nozzle. It starts at velocity equals 0, and since it travels at low speeds, we can regard the flow as incompressible. So as the cross-sectional area decreases, we find that the velocity increases. And it increases until it hits the throat, where the Mach number becomes 1, exactly 1. Next, if you remember our flow regimes, once it gets to Mach 1, the flow is no longer slow and can be considered supersonic. And once you get to supersonic flow, the flow becomes compressible, and density is no longer constant. And when you get to a flow where density is no longer constant, some weird things happen. But it may seem counterintuitive, but as you now traverse through the divergent nozzle section, the flow actually accelerates again. And depending on the cross-sectional area at the end, you can achieve whatever desired speed you like. And in case of the Rutgers wind tunnel, it's 3.45. And finally, what is Schlieren? So, Schlieren is basically the variance in densities of certain objects that are most likely invisible to the naked eye. So as you can see, in this example, we have a candle, and the candle is emitting smoke. And you can see that at some areas, it's more dense than others, which you can tell by the different colors. And some areas of the smoke are less dense than others. And this inherent difference in density is known as Schlieren.
For our project, when we were gathering Schlieren images, we used this set of mirrors which were arranged around a transparent section of the middle of the wind tunnel. A strobe light passed light between these mirrors and through the transparent section, creating a Schlieren image, which was then sent past a knife edge to dull the picture, and then into a camera where this footage was analyzed in our computer. When we were designing our models that we were going to place inside of the wind tunnel for our project, we had 3 objectives for what we wanted these models to accomplish. The first was that we wanted them to verify the National Advisory Committee for Aeronautics tables on what types of shock waves are formed for cones at different angles. They have different angles to their axis of rotation. This is a picture of that table. Each line represents 1 Mach speed, and then the x-axis is the angle from the axis of rotation of the cone that's being tested. And the y-axis is the angle from the axis of rotation of the shock that that cone should form. The other two objectives that we had for our models were that the second one was that they verified standoff equations. So Eric didn't mention this before, but there are two different types of shock waves. There are attached shocks and detached shocks. Attached shocks form an angle from the point of the cone, and those in our wind tunnel at Mach 3.45, these are commonly found. Attached shocks can be found at angles equal to or less than about 38 degrees. At any angle from the axis of rotation larger than that, you form detached shocks, which are rounded off and have a subsonic pocket that forms between the face of the model and the shock itself. So we wanted to also create, although most of our models would end up being models that we expected to form attached shocks, some of them we expected to form detached shocks. And we wanted to see how the diameter of these models affected the distance of the blunt rounded shock that formed in front of the face. The third objective for these models was that they be unique and incorporate some sort of design where we wouldn't know what to expect. We understood quite well how attached shocks work and how detached shocks work, but we wanted situations where we couldn't be quite sure what would happen, so we designed some of our models that way. These are the four original models that we designed. The first in the upper left is a double cone. We expected 2 attached shocks for that model. The bottom left is the ridged cone. This is one that we designed not quite sure what would happen, but expecting that we would see attached shocks at each of the ridges and at the point in front. The upper right is the cone cylinder with flare. We expected all attached shocks there as well. These all have different angles at their front face, so that we would see we'd be able to test different parts of the NACA table shown before. And then the bottom right was my model, and that was a blunt model. So we wanted to see how far off the detached shock would form from the front face of the model.
Now to transition from theoretical values to our actual results. In the first model, you'll see an attached shock wave off of the first cone. Now, the top of it's not quite clear because this model is actually shaking in the wind tunnel, so that caused some problems, but it still did form a lot of interesting shock patterns. You can see a second shock coming from the far left of the picture, and that formed from what's known as a boundary layer at the bottom of the wind tunnel, and that's a region where the velocity is 0, so it acts almost as a wedge and forms another shock wave. Now, the attached shock from the front cone and the boundary shock combined it into a Mach stem. It's very tiny. It's a small vertical section near where those two shocks meet, and they let off, and another attached shock went down the picture. The second model was a ridge cone. That again formed an attached shock. We actually expected 3 attached shocks to form, 1 off of each ridge, but only 1 formed. They all combined together essentially. And both of these models formed very accurate results, as they were at most 1 degree off the expected shock angle, and led to percent errors of 2.60% and 0.78%.
And this is the third oblique shock model that we tested. As predicted, it formed 2 shock waves, one at the top vertex and one at the frustum portion of it. And what's different about these shock waves is that they don't come completely flat off of the vertex. What happens is there's something called expansion fans that form. Basically, what this happens is flow, when it rounds off a corner and goes from smaller cross-sectional areas to larger ones, the temperature, density, and pressure all decrease, and this causes a sudden change in velocity, causing expansion fans to, well, quite literally fan off of the corners. And that's what's causing the sort of rounded shape that you can see on the shock waves. Also, what you can see here on the far right of the picture, if you look in the corner, what happens there is the shock wave is interfering with the layers on the wind tunnel itself, and the waves are reflecting off. And here we had a little bit more percent error than usual, about 7%, but that's still pretty accurate. And this is our blunt model, the first one that we tested. Now this model, the way it was created was there's a front face, and there's angles starting at 50 degrees tapering off to 0. And we were able to treat this as a spherical object in the front. So here we used a spherical equation for standoff distances to test what the standoff distance would be. And in terms of the detached shock, Chris was telling us earlier about this subsonic pocket that forms. And in the front of the model, you see a small white section before the black line of the shock wave, and that's basically it. And here, obviously, our model isn't a perfect sphere. There's many angles tapering off. So we did have quite a bit of percent error, but it was only 10%, which is considered a pretty good estimate. Now, to further investigate the standoff distance versus the cross-sectional area of the model itself, what we did was we started with a cylinder here, you can see, and that's 1.5 inches in diameter. And throughout the test, we tapered off the diameter, so here you have a 1.25 inch diameter, and then finally you have a 1 inch diameter. And what our results basically showed was that as the diameter of the cylinder decreases, the standoff distance decreases with it. And this is the equation that we use to show that. So the theoretical values are given here, right next to our actual standoff distances. The equation worked quite well, yielding errors from less than 7%.
In conclusion, we had 5 primary goals. The first was to actually create models for testing in the wind tunnel. The second was to test these models. We also wanted to gather our results and then analyze these results of the shock angles and standoff distances by comparing them to the theoretical values given by the NACA shock table and the standoff distance equation. Our final goal was to actually create a detached shock table for the cylindrical models that showed what the standoff distance should be based off the diameter of the model. And we were successful in completing all of our goals except for the final one because we did find that standoff distance equation, and because we found that, there was really no need to create a table as the equation was simple enough to find the values easily. And there were a couple possible improvements that we could have made. First, we could have tested a greater number of diameters for the cylindrical models because we really only had a ½ inch variation, and that's not too much to really see if the NACA equation worked, or the standoff distance equation worked. And the other improvement we could have made is we could have tested a greater variety of angles for our cone-shaped models because we only had a few different angle values, so we really weren't verifying the NACA table as well as we could have. And for further research, we could test our models at different Mach numbers, so maybe at different wind tunnels, because the shock patterns could vary greatly in hypersonic flow or transonic flow, or even at different supersonic Mach numbers. And now to move on to acknowledgements. First, we would like to acknowledge Mrs. Rosen and Jean Patrick, who made this whole Governor's School program possible.
And our project mentors, Professor Doyle Knight and Anthony Ho, who are both in the audience. And as well, our RTA, John Schaefer, who is there with us every step of the project.
Finally, we'd like to thank our sponsors, Rutgers University, the State of New Jersey, Morgan Stanley, NJ Resources, South Jersey Industries, PSENG, and the GSET alumni community.
So, thank you for listening to our presentation. If you have any questions, we'd be happy to answer them.
That's a question.
Yeah, go ahead.
I'm a bit confused if you could elaborate a little bit. Why speed in the wind tunnel increases after this narrow portion of it? When you reach track
Eric,
1?
go ahead.
Alright,
I'll go back to that slide as well.
It's kind of very
It is very counterintuitive. Alright, there's something called the continuity equation, if you've ever heard of it, and it basically states that the product of the density, the area, and the velocity remains constant throughout the flow. So in the beginning, the reason why velocity increased is because we said that because it was traveling slowly, it was incompressible, and that meant the density remained constant. So if the density remains constant, we only need to consider the product of area and velocity. It remains constant. So as area decreases, velocity must increase. All right, but once
Bernoulli's law, right?
Bernoulli's equation doesn't apply to compressible flow. So it's
called the continuity equation. Bernoulli, yeah.
I should also say it's extremely pressurized on the left side.
Alright. Okay, so when you move on to the divergent section of the nozzle, we get compressible flow, which means density is variant. So now we have to consider density in our product. So the cross-sectional area increases, and we said the velocity increases as well, right? So that means the density has to decrease faster than the velocity increases. So that's what happens.
Yes?
What's the practical application of this in the real world? Why do you care?
Do you want to do that?
Why should we care?
So one question you might have thought of before is why have the speeds of commercial airplanes not increased in the past 60 years? And right now they travel about 0.8 Mach, and the reason behind that is once you start to get close to the speed of sound, there's the chance that shock waves could actually occur, and that would result in a significant increase in energy and power needed to fly the plane, and so that would increase the cost by nearly 10 times, and consumers just aren't willing to pay that. So the practical application of shock waves happens basically in commercial flight, why it hasn't advanced as technology has.
Sure. Yeah, I can think of other examples too. There's also other technologies, perhaps the future of probably not commercial air travel, but air technology in general will rely a lot on supersonic travel. And so an example that our project mentor brought up with us as well was scramjet technology, which has been around for a long time, but it's never been considered, ramjets have been, but never been considered feasible for commercial use or for commercial industrial application. But and if that technology is to be advanced with scramjets, which are combustion ramjets, supersonic combustion ramjets, it will rely a lot on this type of research and technology.
Yeah.
How large were the actual models that you made, and how big is this wind tunnel?
Well, the wind tunnel is actually, it's a 10-inch by 10-inch.
Six.
Oh, 6, well, okay, there's a 6-inch by 6-inch testing area. So if you want to go back to the diagram, just keep going. Oh, yeah, I'll go back. Okay, so this area right here is 6 inches by 6 inches, and our models themselves were usually anywhere between 3 to 4 inches in length and anywhere between 1.5 to 2 inches in diameter. Anyone else?
Okay, so that concludes our presentations for